I want to introduce you to simple harmonic motion. This is the beginning of chapter 15. Okay, so in this chapter, we're considering various different systems moving with periodic motion. And the simplest system to consider, the one we're going to start with, is a mass on a spring, okay, so with no friction. So I want to show you a simulation of that and point out a couple of features. Okay, here we are inside a simulation of some masses on springs. So we can take a mass here and hook it onto a spring if we like. And I just want to show you first, we can show the natural length of the spring. And now I'm going to hook on a 100-gram mass, and it's going to have a new equilibrium position actually now, which I can show here in green. And this mass, because there's no friction at all, will just keep bobbing around about that equilibrium position. So this is periodic motion because it continually does the same thing. It goes back and forth, back and forth. Now, whenever we have periodic motion, we can talk about the period of that motion. So if I pause this for a second, if you think about the time that it takes to complete a full cycle, so from somewhere above the line, say, actually, let me make this slow. From here, back down to here, right? That was one cycle. So the period is defined to be the time for one cycle, that's capital T, and frequency is 1 over the period. We also have something called angular frequency, which is really the same thing as an angular speed in a way, and that is 2 pi times the frequency f. The other thing we can talk about here is the amplitude of the oscillation. So the amplitude, let's let this go a little faster. The amplitude is how far this mass is going at its maximum displacement from the equilibrium position. So let's get something else going that has a bigger amplitude. Okay, so this has a much bigger amplitude than the one on the right. Right, there's a much bigger displacement from the green equilibrium position. You probably also noticed that these two springs are oscillating at very different frequencies. And every system of spring and mass has its own frequency, and that it will oscillate at naturally. We sometimes call it a natural frequency. And it has to do with the mass and the stiffness of the spring. So here we've got two springs that have the same stiffness, but they have different masses on them. So they have different natural frequencies. If I take that 50-gram mass off and put on a larger mass, let's let them go again. Right, you can see that that 250-gram mass is moving even more slowly. It has an even longer period than the 100-gram mass. I can also change the spring constant, so I'm going to make one spring constant large, and oh, things changed again, right? So the natural frequency depends on both the spring constant and the mass. Okay, you saw a couple things in that simulation. I tried to point out the frequency of an oscillation. That's an important concept. The units of that are hertz, where there's how many oscillations per second. And then the time for a full cycle is a period, which is 1 over the frequency. I also pointed out, and I'll get to this again later, that the angular frequency is 2 pi times the frequency f. Okay, when you have some kind of periodic motion like this, we can model it with a sinusoidal function. So it can be a sine or a cosine. Those are just shifted versions of one another. So x of t is equal to xm, which is some amplitude, okay, the maximum distance that the mass in this case can go from the equilibrium position, times a cosine function. And in the cosine function, we've got omega, which is 2 pi f, so the angular frequency. We've got the time, and we've got this thing here, we call this a phase shift. This adjusting that number lets us shift the cosine function around with respect to the origin along the x-axis. So why a sinusoidal function for a mass on a spring? I have another video here that I hope you'll enjoy that shows this. Mass on a spring, paper, spray paint, and you get a sine function. Okay, so we've got the motion described by cosine function, and I want to go through all the pieces of this equation. So this first piece, x sub m, this is the amplitude. This is the maximum displacement value from the equilibrium position. So if we draw a little cosine function here, the amplitude xm would be given by this distance here, or you can think of it as this distance here. And this is also often written as just the capital letter A for amplitude. Okay, the thing that's inside the cosine function, so the argument of the cosine function, we call that the phase, and this part here is the phase angle or phase constant. And what you need to know about this is that if this number is positive, that means that the function will be shifted to the left compared to just a regular cosine function. And if phi is negative, that will shift your function to the right. Okay. And then I've mentioned the angular frequency omega before. You can think of it as 2 pi over the period or as 2 pi times the frequency. Okay, and here's another just picture of that same image with all of the parts labeled. We're going to be coming back to this equation a lot, so how's it sound slide? Okay, this group of slides is intended to help you visually recognize all the different aspects of that equation. So if you look at this first graph, A, we've got two different cosine functions shown there, one in blue and one in pink, and there the amplitude is the thing that's different, right? The distance between the equilibrium position, the 0 line, and the highest point is different for the pink and the blue, but those curves are otherwise the same. Over here in graph B, you can see that the amplitudes are the same, and they both start from their maximum amplitude, so they're both cosine functions with no phase shift, but they have different periods, right? The blue one, to go from one full cycle, goes from here to here, and the pink one, to go one full cycle, just goes from here to here. Okay, so they have different periods. That means they'll have different omegas. And down here, the blue and the pink have two different phase shifts. So the blue one has a phase shift of 0. That means it's a pure cosine function, right? X starts at the full amplitude. Whereas the pink one is shifted to the right, okay? And you'll notice that it's got a negative on that phase shift, right? And I said before, a negative phase shift will correspond to a shift to the right. Okay. Now, when we have this function, x of t equals xm cos omega t plus phi, we can take time derivatives to figure out what the velocity and the acceleration are. So let's take a first time derivative. And what you get when you do that is, well, you get the maximum, the amplitude back, the maximum displacement. Your cosine is going to turn into a negative sine. And then we need to multiply by the time derivative of the argument of that sine function. So we're going to multiply by omega. And rearranging things a little bit, I end up with negative omega xm sine omega t plus phi, which is what's written down here. I just wanted to show you how we got there. Now, if you like, you could rewrite this equation like so. You could write it as this, where I've grouped together this omega and this xm, the things in front of the sine function, because those represent the velocity amplitude, the maximum velocity, okay? And I could rewrite my velocity equation as I have at the bottom here, with this Vm being equal to omega times xm. Okay, we can go one step further. We can also take a further time derivative to get the acceleration. When you do that, right, you've got I had a negative sine function for the velocity. So when I take another time derivative, the sine becomes a cosine, but we don't change the SIGN sign. It's still negative. And you get another factor of omega out front. So you end up with negative omega squared times xm times cos omega, oh, there's a t missing here, plus phi. And what you might notice is that this part is simply x as a function of time. Okay, so you could rewrite it this way, that the acceleration is equal to negative omega squared times x. And this turns out to be really useful. One way you can think of it is actually as a differential equation. You won't learn how to do differential equations properly for a while, but just to give you a taste of what this is an equation that relates the function itself to its derivatives. We call that a differential equation. And that's what we have right here, right? We have a second derivative is equal to negative omega squared times the function itself. And you'll learn eventually to determine what the solutions of this equation are. But one of the solutions is what we've been talking about. X of t equals xm times cos omega t plus phi. Okay, that's one of the solutions to this differential equation here. On this slide, I've got plots of the displacement x, the velocity v, and the acceleration a as functions of time for a pure cosine function. So these graphs are shown for phi equals 0. Okay, so you can see here's the displacement. It looks like a cosine function, and its amplitude is xm. You can see that on the graph. Here is the velocity. So it is a negative sine function, right? A positive sine function would start by going up. This one starts by going down. And the value Vm is equal to omega times xm. And then the last graph is the acceleration. It is a negative cosine function, so it starts from the negative of the amplitude, and the maximum acceleration is omega squared times xm. So if you look at the top and the bottom graphs, right, they just look flipped compared to one another. They're the negative versions of one another. Plus, the bottom one has been scaled by omega squared. And that middle graph is a sine function instead of a cosine function. So when you have extreme values in the first graph, so when we're at our largest values or smallest values of displacement, those are going to correspond to 0 values in the velocity. And if you think about a mass on a spring, when the mass is the furthest that it gets from the equilibrium position, it's actually stopped, velocity 0. So it all makes sense. And then if we go down to the final graph, those same points are again going to correspond to maximum values of acceleration. And this also makes sense. If you think about your mass on a spring and it's at its furthest position from the equilibrium value, that means it's the most stretched. That means if you think of F equals negative kx, that means there's the most force. So there's the most acceleration for that mass. All right. Yeah, just to connect back to Newton's second law for a second here. So the net force is equal to ma. A, we've discovered we can write as negative omega squared times x. So if you kind of put the m and the omega squared in a bracket here, you end up with F equals negative omega squared times x. But we're dealing with a mass on the spring. So F equals kx. But these two equations must be, negative kx. But these two equations must be equal to one another, right? They're both the net force. So that tells us that k is equal to m omega squared. In other words, omega is equal to the square root of k over m. And earlier on, I talked about natural frequencies of objects, how those depended on the spring constant and the mass. And here's the relationship right here. Okay, so omega equals square root of k over m is given here, and the relationship with the period is given here. And how you get from this equation to this equation is simply by using omega equals 2 pi over t.